Okay, so this is the second video for Unit 4. We'll look at transformations, and the good thing about transformations is that these follow exactly the same way they did for the parabolas. So this right here tells us that it is a reflection over the x-axis. So if it is a negative, it's going to reflect over the x-axis. The value of A right here is a stretch if it's greater than 1, and it is a shrink if it's less than 1. I might need to zoom out some. Hold on a minute. All right. This H right here tells us that it is either a movement right or left. It's right if it's negative and it's left if it's positive. It's always opposite when it's with the x. And then this value of k right here tells us that we are going to shift the curve up or down, and it depends. If it's positive, we'll shift up. If it's negative, we'll shift down. All right, so looking at number 11, we are asked to describe the transformations. So keep in mind that we are dealing with exponential functions, and so that means that the base is a number, so we have to have a base. So that right there is 3. So we are going to use y equals 3 to the x. Okay, then we are going to shift this graph left 6. So that right there tells me to go left 6. That tells me to go down 4. And then this 2 out in front is the A, so that tells me that it's going to be stretched 2 times taller. So it's going to be a taller, steeper curve. All right, number 12. Describe the transformations of this exponential curve. So again, we always have to have a base number. So in this one, our base function is 1/3 to the x. Now remember, if we have a fraction, we have to have it in parentheses there. All right, so this curve right here is going to shift right 6, and I can tell by that -6. So this one's going to go right 6 and then down 2. Down 2. There's no A value in the front that's being multiplied, so there's no stretch or shrink, and it's not negative in the front either, which tells us that it is not reflected. All right, now we're going to graph. So what I'm going to do is what we did earlier. I'm going to start with the parent graph. All right, so I know that the parent graph of this is y equals 3 to the x. So that if I fill in 0 for x, I'm going to get 1. If I fill in 1 for x, I would get 3. If I fill in 2 for x, that would be 9. So I guess that goes up. And then these are going to be 1/3 and 1/9 and so on. So this is the parent graph right there. Yes, that I'm going to stretch this to be 2 times taller, and then we're also going to shift down 4. All right, so I'm going to stretch because multiplication comes before addition and subtraction. So I'm going to stretch this. Instead of going up 1, I'm going to go up 2, and then I'm going to move down 4. 1, 2, 3, 4. So that point is right there. This is here. I'm going to stretch it 2 times taller, which means it's going to be here. And then I'm going to move down 1, 2, 3, 4. All right, this one is at 9, which would go up to 18, and then it would come down 4 to 14. So that one's still going to be, way up here somewhere. All right, this one over here, if I made it 2 times taller, it would be up there. Like, big deal, right? And then down 1, 2, 3, 4. So that one's going to be right down over here. I think I missed it, but that's all right. 1, 2, 3, 4. No, I didn't. I did a good job. Okay, so now here is the curve, and you can tell that it is steeper than the original one, so it's 2 times taller, and it was shifted 4 spaces down. So what that means now is that our asymptote would be right down here at -4. This time, our parent function is y equals 2 to the x. So I'm going to do a different color so you can see. So y equals 2 to the x. That's the parent graph. All right, so our base number is a 2. So for this one, if I fill in 0, it's going to be 1. If I fill in 1, it would be 2. If I filled in 2, it would be 4, and so on. And then this would go 1/2, 1/4. So here is the parent graph. Now I'm going to do the actual function, and this function, oops, hold on, I'm stuck. This function has been shifted right 3, so we're going to go right 3. We're going to go up 1, and it was also reflected over the x-axis. All right, so first thing that we're going to do is, if we go, we'll reflect it, well, actually, we should go right 3 first. So let's move to the right 3. So 1, 2, 3. Then we're going to reflect it over the x-axis, which means it's right there. Then we're going to shift it up 1, so it's going to be right there. All right, now I'm going to take this point. I'm going to go right 3. 1, 2, 3. Now I'm going to reflect it over the x-axis, which means it's going to be right there, and then I'm going to go up 1. All right, this one right here. Oh, I missed that one. First, we're going to go right 3. So now it's right 3. Then we're going to reflect it upside down, so it will be at -4, and then we're going to go up 1 space. All right, on this one, we're going to move this one right 3. We're going to reflect it over the x-axis, and then we're going to move it up 1. So now I think you can get that the shape of the curve is like this. All right, it should be basically the same size because we didn't shrink or stretch it. We did reflect it, which you can tell it's been reflected, and shift it 1 space up. Okay, growth and decay, hopefully you remember this one. This is always going to be an exponential function. What is convenient about this is that the pattern, the equation is used for growth and decay. What's different is this right in here. So we are going to add if it's a growth, which it would have to be, we would have to multiply by a number bigger than 1 if we're growing. And it's going to be subtraction if it's a decay, which makes sense because we would be multiplying by a number less than 1 if it's decay. The T is talking about the amount of time that goes by. The P, it stands for principal, but this is your starting amount. You could call it your initial value if you want to, if you're doing something that involves money. Okay, number 15, here we go. The mice population is 25,000 and is decreasing by 20% each year. What will be the mice population after 3 years? So first of all, I can tell this is a decay because it mentioned decreasing. All right, I know that the starting value is 25,000 mice, and the R is 20%. So we will say f of x is 25,000. We have 1 minus, this we need to write as 0.2, and then t is in years. All right, so remember the 20%, we can't work problems out as percentages, we work them out as decimals. So 20% as a decimal would be 0.2. We could also write this as 25,000 and then 0.8 to the t. So if you think about it, if you take off 20% from 100, that's going to be 80%. So you could also write your equation that way. All right, now we're asked for the population after 3 years. So what that means is that we're going to fill in 3. So if we take our calculator, and we can type it in as is. So 25,000 parentheses, 0.8, close the parentheses, exponent 3, then we will have 12,800 mice. All right, next up, another population question. The population of a town can be modeled by this equation where T is the number of years since 1990, and that's pretty common. We learned that, especially when we were doing the calculator stuff, that a lot of times we won't use the actual year. We'll just start at a year and then count up. So the question is, what was the population in 1990, and by what percent did the population increase each year? So we were given this equation right here. So this equation, if we kind of take it apart, we can tell that it's a growth because this is over 1. And we can tell that it's a growth of first of all. And we know that the R is 0.04, which means 4%. So we can tell that there was 4% growth each year. And then we also know that the initial population was 6,191. So the population in 1990, so this is the population in 1990, and then it was a 4% increase each year. All right, next up, you drink a beverage with 120 milligrams of caffeine. Each hour, the caffeine in your system decreases by 12%. So how long until you have only 10 milligrams of caffeine in your system? All right, so this one we can tell is a decay because it mentions decreases right here. We know our starting amount is 120 milligrams. We know that it's decreasing at 12%, so we know that this is a decay. So for our equation, I guess I really should write f of t instead of f of x. That was kind of a typo on my part. All right, the original amount is 120. We are going to subtract 12% each hour. All right, another way we could write this would be 120 and then 0.88 to the t, because if we're taking away 12% each hour, that means we still have 88% left. So it's always based out of 100%. So the question is, how long until we have only 10? So what we want to know is, when is this approximately 10? And remember that the t is hours. So what we're going to try and figure out is what hour will we have around 10 milligrams left. So this is really just guess and check with a calculator. There's other ways we can do it with a graphing calculator, but at this point we didn't use those yet. So I'm just going to put 12 and then parentheses 0.8, and I'm going to try 6 hours. All right, that's way too little. So I need to try again. Oh wait, it's supposed to be 120. I can't remember if I did. Oh goodness. Hold on, let's try 6 again. Oh yeah, okay. So that's too many hours. I mean, too many milligrams. Oh my God, I'm so sorry. Okay, so hold on, let me write this because that's a mistake. Whew. Okay, so now I'm going to try 120.8 to the 15th. Oh, that's too little. All right, so I tried 6, was not enough. 15 is too many. So now let's try 180.8 to the 10th. Okay, we can get a little bit closer. So 120.8 to the 11th. Ah, that's really good. All right, we're still technically above 10. So let's try 12 hours, so to the 12th, and now we're definitely under. So we really, 11 hours wasn't enough time, so we really have to wait 12 hours before we can get 10 or only 10. It didn't hit exactly. So somewhere between 11 and 12 hours is when we would end up with 10 milligrams left in our system.